I've used ASAP since 1991 in automotive lighting was my first application. I cut my teeth on that, used it for about 9 years doing automotive illumination, and since then I've used it in a broader general illumination applications. Now I'd like to give you a tour of illumination design in ASAP and show you some of the features, some lesser known features that are really useful in completing illumination designs. We'll also take a look at some specific examples using reflectors, light pipes, and lens-based systems with different sources, including LEDs and incandescent. Today I'm going to show you an automotive lighting system and some other systems. We're going to start with an automotive tail lamp. And typically when we design these systems, we'll receive surfaces from our customer, and what I've just turned on is the part that we're going to be working on the design with. And what you see on the screen right now is actually the finished component with the optical surfaces. However, what we receive from our customer is the lens and the reflector base surface. So this is the package that we need to contour our optics into. And as you can see, we have, in this case, an LED lamp where we have 13 separate LEDs with individual reflector cups. And so we can just kind of shade this up and take a look at the actual part. So these are the surfaces that we received from the customer. And what we're going to do is design in a reflector optic in order to have this lamp comply with the stop lamp and tail lamp test point requirements. So typically when we're designing these types of systems, what we'll start with is some sort of base shape, and we'll build optical facets onto that base shape. So right now, what you're seeing on the screen, the line that I've highlighted is the base parabola, and that was taken. I'm going to turn the reflector back on for a second, and you can kind of see where we're working. We're working in the center cup right now, and I've taken that base shape that they've given us, offset it a little bit, and I'm going to start designing facets into that component. So the construction curves that you see on the screen are actually what I've used then to describe my facet shape. And each segment of the parabola then has a different facet shape developed onto it. And what I need to do now is take these shapes and actually we'll turn this into a surface. So that we have an optical surface that's going to fit inside of our reflector. So one of the reasons that we work in CAD, and I'm working in the Rhino 3D package, you could work in any CAD package such as SolidWorks, CATIA, UGS, any of those packages are acceptable to do this in. One of the reasons that we do that is because we're able to take the customer's data that they've given us, and we can take our optics now and we can manipulate them to interface with the data so that the optics that we're simulating are directly usable inside the part design. So what we would need to do with this particular surface before we go to simulate is that we'd want to trim it back to the reflector surface and duplicate it into the other cup locations. So I've done that ahead of time. And now we have a set of cups that have actually been trimmed into match into the reflector surface itself, so that when we go into our simulation, we're actually simulating the actual system. So in order to get these components in ASAP, we'll take each one of these layers. In this case, this is the optical surface layer, and we just export it, and we're going to use the IGES format. And one of the things inside Rhino is the IGES types have been set up to explicitly export IGES that is readable by ASAP. So there's several types, as you can see, but we can pick ASAP type and go ahead and export that. The same thing's also been done for the reflector component and the outer lens, where we've saved those files ahead of time. Now that we've got an optical surface, we can go into ASAP and convert those into geometry that can be used to simulate the part. So if you recall, we saved our file out of Rhino and we call it OpticSurf4. So I'm going to double click this, and this is going to bring up the IGES translator. We can accept the defaults here, and you can see that we've got our optical surface. Now this translator offers you the opportunity to do material assignments within the translator. However, I'm going to skip that step, and we're going to do the material assignments inside our script, and I'll show you why when we're finished. So we've translated the file, and you can see that we've got a description of the part contained in an ASAP format. I've set up my script file ahead of time to simulate the part, and we're going to simulate the cover lens, the reflector, and the optical surface that we just created. And one of the things I mentioned before is that we skipped the material assignment in the IGES translator because inside my script in ASAP I can use this construct, do-lib construct, that allows me to set my material properties for each one of those components. And what this allows us to do is to change material properties quickly on each one of those components. And we'll look at that a little bit later. So I'm going to run the script file now, and this is going to read in the geometry and read in the sources and begin a simulation of the trace. And we have all 13 LEDs have been positioned into the simulation, so we're going to trace the entire reflector. Going back into Rhino, we're basically tracing exactly what you see in here, and we're simulating that particular performance. And what I have up on the screen is a ray trace plot showing a section of the part, and you'll see as the trace progresses that there'll be 13 different sources that will be traced out of each different cup. Okay, so we've completed the ray trace, and what we've done in ASAP is ahead of time we've set up a test point output. This is in the pattern of the stop lamp pattern, so if you're familiar with automotive test lamp patterns, the test points have been laid out in kind of a grid that simulates the angular distribution. We can look right away, we see that at the HV point, the 00 point, we have around 210 candela. That's a little bit high, so maybe we want to revise that design based on those outputs. What we've also put out, which may be a little more familiar, is an isocontour plot in the angle space of the turn signal, so we can look at the angular contours, as well as a picture plot where we can interrogate individual pixels if we want to look at specific values. And you'll notice that the resolution for this particular demo is a little bit low. We've traced a smaller number of rays than we would normally trace for an entire simulation. If we wanted to do the final output on this, we would run upwards of 3 million rays. In this case, we've run only a couple 100,000. The 3 million ray trace might take 45 minutes to an hour to complete. So based on that information, we might go back and want to revise our design. And that's just simply coming back into Rhino here, and we're going to recreate another design section. Again, we have our base parabolic curve that we were working on, and then I've reconstructed the segments to direct the light. In this case, putting a little bit more left-right spread so you can see the surfaces have been tipped a little bit. And the process to check this one again would be the same as we followed before. Would simply revolve this surface into a complete surface, and then we'll trim it off to the reflector. So I'm going to show you the completed trim reflector. So that's the completed reflector design. Again, it's been matched up to our reflector components. So now this is a completed part that can be given back to the customer if the optical performance is acceptable and it meets all of the packaging constraints that we've been given. So again, all we need to do to analyze this is we're going to export those components to an IGES file using the ASAP format. We'll come back into ASAP, do our conversion. Again, we're going to leave the material assignment off. And to run our new design, we just simply need to substitute the name of the new file, and we can rerun the design. And we'll get a new set of plots with the new reflector, and we'll get a new test report at the end of the simulation. Okay, we've completed the stop lamp trace, and you can see now that we've lowered the center value, and that's what we were trying to do with our change. And so we've got the information that indicates that the design is acceptable. And again, we have our plot where we can interrogate individual pixels, or we can also view it with the ISO contours. I mentioned up front that I didn't do the material assignment to the geometry with the IGES translator to allow me to change the parameters of the design quicker. And one of the things that I've set up in this particular file is we have roughness models that simulate different surface finishes, one of them being a simple model for just simulating injection molding parts, because they're not going to be perfect, so it simulates a modest amount of slope error. The other thing that I've got set up in this particular file is a texture. For those of you that are familiar with injection molded parts, a lot of times they'll put on something called stipple or mold tech finishes, and actually in this case I've simulated that reflector using that texture. If I wanted to find out what the performance is without that texture, I simply have to change my model back to just the bare molded slope part, and I could rerun my simulation and have that result. Okay, the next demonstration we're going to take a look at is a demonstration of using ASAP for architectural type lighting. And I'm going to open a file. In this case, we're going to analyze a roadway luminaire. So we're going to have a situation where we're going to have the lamp and the street, and we're going to take a look at the output from the lamp. I'm going to walk down through the script and just point out some of the things in the script that we've set up. In this case, we're going to model an HID street light. So we've got an arc tube modeled as well as the source envelope. So we've got the geometry of the source is going to be included in this. So if we pass any light back through the source, we're taking those interactions into account. And then we're going to read in some geometric components a housing. The design of this is composed of a formed reflector that's manufactured using the Miro 4 Alinod material. We also have a piece of the reflector that's going to be the stucco material, which, if you're familiar with that, it's a bumpy material, so we're going to model that bumpiness inside ASAP. We've got a cover lens, and then we're going to set up the lamp on a pole and mount it above the street and look at the output of the lamp on the street itself. After that's done, it's also going to take and put 4 lamps in a corner arrangement to show the actual arrangement of the lamp as though we were lighting roadways. So I'm going to go ahead and start this file and then talk about the output. Okay, the first thing that you're going to see on the screen is the simulation of the actual architectural luminaire. So we have the HID source with the geometry included, and in cross section you can see the reflector that's been designed for this particular case, and then we have the housing and the glass and the pole that's holding the part. In the plot that you see before you, we're tracing a limited number of rays to the screen. We're actually tracing more rays to simulate the output, and we're limiting the rays on the screen in order to keep the screen clear. Okay, you're going to see several plots come up on the screen, and we'll go back to each one of the plots and explain them. Okay, so the first plot is actually a luminance plot of the individual lamp on the ground, and it's expressed in foot candles, and we've shown the contour. So the ground is labeled here in inches divided into grids, and you can see the output of the lamp in that format. And then we've got a plot of what we call the type C photometry of the lamp. For people that are familiar with that, this would be as though we'd photometered the lamp in the lab. And this particular lamp was designed to be a full cutoff lamp, and this plot is showing us that we do not have any light above any uplight, and that we are meeting the full cutoff criteria. And then this is also an isocontour plot of 4 lamps positioned at each corner, so we can see the illuminance that we would have if we had used 4 of these lamps to light a roadway section. We also have each one of those plots in a 2D plot viewer where we can go in and interrogate each pixel individually and find the values of the points. Now, this particular plot happens to be a plot that's been adjusted to simulate what you might see with your eye, as though you were hovering above the pattern. This is a nice isolux plot of the 4 lamps, and then this is the plot of the 4 lamps positioned over a roadway section. So one of the useful things that we can do inside ASAP is we can combine these plots into a 3-dimensional view, and I'm going to show you some of that. And we'll start by looking at what we're showing here is the lamp housing, and we have some rays being traced out, so we can hide this cover, and we can see the ray trace that we saw in 2 dimensions. We can see that we were doing a full 3-dimensional ray trace on our geometry and the rays that are coming out onto the street. Now, what we saw inside ASAP was a 2D plot of the isocandela, and what we can do here to add a little bit more realism to the trace is we can show that plot in 3 dimensions with the isocandelas overlaid. So it gives you a little bit more of an idea of the actual distribution of the light on a street plane. As we mentioned before, we also plotted the distribution of 4 lamps, so we can look at that in 3-dimensional space. So if you imagine 3 more lamps here, now we can see that we have the output of those lamps, and this is actually something that we can interrogate, so we can find the foot candela values along this section of roadway that we've lit up with 4 lamps. If we want, we can change this into grayscale to give a little more realistic output. We could also switch over to the lit appearance view in grayscale to give a little bit more of a realistic picture of what the output from these particular lamps will be on an actual roadway space. In this next demo, we're going to cover some of the extended capabilities of ASAP. One of the things that's useful for illumination systems is to be able to optimize the system. And in order to do that, we're going to use some scripting capability that's built into ASAP that has functionality outside of ASAP. So within the ASAP editor, we can actually choose to use not only ASAP script, but several other scripting languages. One of the most common languages is the VB script. Another one that has extensive capability is Python. And it's very simple to use these within ASAP. We simply select the script language that we want to use, and then we begin typing in that script language. So this is an example of a VB script, simple hello world program. We type it, we run it from the editor, and we can see that we're operating in VB script now. For the illumination system then, we've actually written a VB script file that contains a downhill-simplex method. If you're familiar with optimizations, the downhill-simplex is one that's commonly used for illumination. So the downhill-simplex code has been written into the VB script file, and we can combine that with our ASAP file to do the analysis of the illumination system, and we're going to feed back the information from the analysis into our downhill-simplex, and the downhill-simplex is going to continue to run the ASAP analysis until we have optimized the system based on the criteria that we've given it. So very quickly, what we have in front of us in our ASAP script file is simply a source, and then we're going to build some geometry, and what we've done is we've put in some variables for the points that describe this curve, and then this curve is going to be swept into a reflector. We're going to trace that reflector, and then we'll have a merit value calculated at the bottom. In this case, we're simply going to use the center intensity as the quantity that we want to optimize. So to use this, what the user needs to specify is the number of parameters that we're going to manipulate. So in this case, we're going to manipulate these 3 point values to change the shape of our reflector. And then we need to give it an initial guess of where we think the design is going to be in the simplex method, and some range for the variables to operate in. Once we've defined that, we can simply run the file, and the ASAP will take over and begin the optimization. I've included some plot output, which you normally would not do during an optimization, but for this demo we're going to continually plot the output to the screen so that you can see the changes in the part as the optimizer works on the component. So what you're seeing on the screen right now is the first you'll see a simulation of the rays being traced, and then the second plot will be the intensity plot for the system under evaluation. And the ASAP is automatically running the simulations and changing the geometry each time in order to try and maximize the intensity at the center point. If you recall the first simulation of the component, right now we're seeing center values of around 80,000 candela. The first simulation of our component had center values of around 29,000. So the system's increased fourfold in performance automatically through the optimizer. Okay, so the optimizer's completed running through its iterations. In this case, we asked it to only run a maximum number of 50 times. We could set that number higher if we wanted to be sure that we were finding the minimum. However, we've settled on a design that's given us 4 times the performance that we had originally. And now we can just query ASAP. We use the reg command for each one of our values. And these are the values of the parameters in our curve that we can now substitute back into our design that will give us that optimum performance. All 3 of the demonstrations that you've just seen were done on a typical desktop computer. In particular, this one uses an AMD Opteron with 2.19 gigahertz. The computer has 2 gigs of RAM.